The last special case I want to look at is the case where the Q factor is 1 over the square root of 2. What's interesting about this one becomes apparent when you start looking at the maximum value of the amplitude response. If you work out where the poles are in this case, you'll find that the poles are at an angle of 45 degrees to the real axis, and as all complex poles are, they are a distance of the resonant frequency away from the origin, so their amplitude is the resonant frequency. Imaginary real axis. Right, so what's interesting about this? Well, we have discovered so far that the frequency response, or rather the amplitude response, of these second-order systems that we've been looking at can have a resonant peak, a value above 0 dBs at certain frequencies, usually somewhere around the resonant frequency. They're always slightly below the resonant frequency, but somewhere in that vicinity. What we haven't done so far is worked out what that maximum value actually is. We do know that the value of the gain at the resonant frequency is given by the Q factor, but the maximum value of gain doesn't occur at the resonant frequency. It occurs before the resonant frequency, at a lower frequency. So what actually is the maximum gain that you can get? Well, to do that, we have to go back to the expression for the frequency response and start looking at what frequency that maximum occurs at. Here's the expression for the frequency response. If I'm interested in a maximum value, then what I'm interested here is a case where the denominator of this expression here has its minimum possible value, because that will give me the maximum value of the frequency response, or the amplitude response anyway, the modulus of it. So what I'm interested here is the minimum value of the magnitude of this denominator. I've called it den in the slide, short for denominator. And the magnitude of the denominator I can get from Pythagoras, noting that this term here is actually real. So the real component of this denominator is 1 minus omega squared over omega naught squared. The j squared is just minus 1. And the imaginary component is omega over q omega naught. So if I take the real component and square it, and take the imaginary component and square it, and add them up, that will give me the square of the magnitude of the denominator. It's just Pythagoras again, in a right-angled triangle. So the square of the magnitude of the denominator is 1 minus omega squared over omega naught all squared, plus omega naught squared over q squared, oops, that's just an omega, sorry, omega squared over q squared omega naught squared. Now if I'm looking for a minimum value of this expression here, I can get that by differentiating it with respect to frequency and setting that equal to 0. I'm looking for a turning point. So d denominator squared differentiated with respect to frequency is, well, this term here would give me 2 1 minus omega squared over omega naught squared times minus 2 omega over omega naught squared. And this term here would give me 2 omega over q squared omega naught squared. And for a turning point, that must be equal to 0. So I would get 2 1 minus omega squared over omega naught squared times 2 omega over omega naught squared equal to 2 omega q squared omega naught squared at the turning points. 2's cancel, those omegas cancel, those omega naught squareds cancel, and I'm left with 1 minus omega squared over omega naught squared equals 1 over 2q squared. And that gives me that omega squared over omega naught squared is 1 minus 1 over 2q squared, and therefore that omega, the frequency at which the maximum actually occurs, is omega naught times the square root of 1 minus 1 over 2q squared. And if I wanted to know what my maximum gain actually was, I could take this value of omega and substitute it back into the expression up here. But for now, I just want to note something interesting about this formula, which is that it doesn't have any roots if q is less than 1 over the square root of 2. You can see that by considering this square root here. In order to get a real frequency out the end, this square root here must be the square root of a positive number. So 1 over 2q squared must be greater than 0. And that means that 2q squared has got to be greater than 1, or q has got to be greater than the square root of a half. And if it isn't, if q is less than that, then there will be no real frequency for which there is a maximum value of the gain in the amplitude response. In other words, q of the square root of a half is the biggest value of q for which there is no peak in the amplitude response. And the usefulness of this result, it perhaps comes apparent if you look at this series of curves here. The q equals 1 over root 2 is this one here. You'll see that the gain remains at 0 for as long as possible before it starts moving down. Now, if you're designing a low-pass filter, a filter that passes low frequencies but cuts high frequencies, then you'll often want to maintain the gain of the frequencies of interest to be as close to 0 as possible until you get to something called the cutoff frequency, and above the cutoff frequency you want all the frequencies to be attenuated. Choosing a value of q of 1 over root 2 allows you to maintain that gain as close to 0 as possible for as long as possible before the attenuation starts pulling down, without introducing any peaking in the response, any maximums. And it's one reason why this is a very common choice for low-pass filters in a lot of audio applications. The response is very similar to the case of a Q factor of a half, but if you compare the two side by side, you'll find that this value of Q keeps the gain at 0 dB for longer. Compare this one with Q of 1 over root 2 to this plot where Q is a half. That brings us to the end of these special cases, these particular values of Q that I wanted to discuss. Next time we'll look at a slightly different circuit, a bandpass filter.